Alright, let's work through this geometry problem together, and this time I want you to pay close attention to one simple idea that makes the whole problem fall into place. We have an equilateral triangle PQR inside a circle, and the point O is the center of that circle. The point O lies directly on side QR. We're told that every side of the equilateral triangle has length 13 units. The distance from Q to O is 5 units, and the distance from O to R is 8 units. Our job is to find the area of the circle. And just a quick reminder before we start, the diagram doesn't have to be perfectly drawn to scale, so don't try to estimate lengths or angles just by looking at the picture. We're going to trust the information given in the problem and use geometry to uncover the radius. Now, let's begin with the most important question. What do we actually need in order to find the area of a circle? Well, the area formula is pi times the radius squared. So if we can find the radius, or even better, if we can find the radius squared directly, we're essentially finished. Since O is the center of the circle, any segment from O to a point on the circle is a radius. Point P is on the circle. So let's consider the segment PO. I'm going to call the radius R. That means PO equals R. Notice something useful here. We don't actually need to find R itself if we can determine R squared, because the circle area formula uses R squared. So our target is really R squared. Now let's take a careful look at the equilateral triangle PQR. An equilateral triangle is a triangle in which all three sides have the same length, and we're told that each side is 13 units. So we have PQ equals 13. QR equals 13, and PR equals 13. But there's another very important property of an equilateral triangle. All three of its interior angles are equal, and because the angles of any triangle add up to 180 degrees, each angle must be 60 degrees. Therefore, angle PQR is 60 degrees, angle QRP is 60 degrees, and angle QPR is 60 degrees. And this is exactly the information we need. Since O lies on the side QR, the segment QO points in the same direction as QR, so the angle between PQ and QO is the same 60-degree angle. In other words, angle PQO equals 60 degrees. At this point, we can focus entirely on the smaller triangle PQO. And before we move forward, if this way of breaking a geometry problem into smaller, manageable pieces is helping you, take a second to like the video, subscribe to the channel, and leave a comment telling me whether you would have noticed the 60-degree angle immediately. It really helps the channel, and more importantly, it tells me what kinds of problems you want to see next. Now, back to the problem. In triangle PQO, we know three important pieces of information. The side PQ is 13 units, the side QO is 5 units, the side PO is our unknown radius R, and the included angle between PQ and QO is 60 degrees. So what theorem should we use when we know two sides and the included angle and want the third side? Exactly, the law of cosines. Let's briefly recall what the law of cosines says. For a triangle with two known sides and an included angle, the square of the opposite side equals the square of the first side plus the square of the second side, minus 2 times those two side lengths multiplied together, multiplied by the cosine of the included angle. It's essentially a more general version of the Pythagorean theorem, and when the angle happens to be 90 degrees, the cosine term becomes 0, and we recover the familiar Pythagorean theorem. Here, our included angle is 60 degrees, so we can apply the law of cosines directly to triangle PQO. The side opposite the 60-degree angle is PO, and PO is our radius, r. Therefore, r squared equals 13 squared plus 5 squared minus 2 multiplied by 13 multiplied by 5 multiplied by the cosine of 60 degrees. Now let's simplify this carefully rather than rushing. 13 squared is 169, and 5 squared is 25. So we have r squared equals 169 plus 25 minus 2 multiplied by 13 multiplied by 5 multiplied by cosine 60 degrees. Next, 2 multiplied by 13 gives 26, and 26 multiplied by 5 gives 130. So the expression becomes r squared equals 169 plus 25 minus 130, multiplied by cosine 60 degrees. Now, 169 plus 25 gives 194. Therefore, r squared equals 194 minus 130 multiplied by cosine 60 degrees. And here comes another standard value that is worth remembering. The cosine of 60 degrees is 1/2. So we substitute 1/2 in place of cosine 60 degrees. That gives us r squared equals 194 minus 130 multiplied by 1/2. 130 multiplied by 1/2 is 65. Therefore, r squared equals 194 minus 65. Subtracting gives us r squared equals 129, and that's a very important result. We have found exactly what we wanted. The square of the radius is 129. Notice that we didn't even need to calculate the radius itself. We could say that the radius is the square root of 129, but that would actually be unnecessary because the area formula needs r squared. Before we finish, though, I want to verify our result using the other side of the triangle. This is a really useful habit in geometry. Whenever the figure gives us another independent way to calculate the same unknown, checking it can catch mistakes and give us confidence that our answer is correct. So, now let's look at triangle PRO. In this triangle, PR is 13 units and RO is 8 units. The remaining side, PO, is again the radius r. Because PQR is equilateral, the angle at r in the original triangle is 60 degrees. Since O lies on QR, the angle between RP and RO is also 60 degrees. Therefore, angle PRO equals 60 degrees. Once again, we have two sides and the included angle, so the law of cosines is the perfect tool. The side opposite the 60-degree angle is PO, which is r. So we write r squared equals 13 squared plus 8 squared minus 2 multiplied by 13 multiplied by 8 multiplied by cosine 60 degrees. Let's simplify this carefully. 13 squared is 169 and 8 squared is 64. So r squared equals 169 plus 64 minus 2 multiplied by 13 multiplied by 8 multiplied by cosine 60 degrees. Now, 2 multiplied by 13 gives 26, and 26 multiplied by 8 gives 208. Therefore, r squared equals 169 plus 64 minus 208 multiplied by cosine 60 degrees. Next, 169 plus 64 gives 233. So we have r squared equals 233 minus 208 multiplied by cosine 60 degrees. Again, cosine 60 degrees equals 1/2. Substituting that value gives r squared equals 233 minus 208 multiplied by 1/2. Half of 208 is 104, so we get r squared equals 233 minus 104. That gives r squared equals 129. Perfect. We have arrived at exactly the same value from the second triangle. That agreement is a strong confirmation that our calculation is correct. Both triangle PQO and triangle PRO lead us to r squared equals 129. Now we're ready for the final step. We want the area of the circle, and the standard formula for the area of a circle is pi multiplied by the radius squared. In spoken form, we can say area equals pi times r squared. We already know that r squared equals 129, so there's no need to find the square root of 129. We simply substitute 129 into the formula. Therefore, the area equals pi multiplied by 129. Rearranging that slightly, we can write the exact area as 129 pi square units. That is our exact answer. If you want a decimal approximation, we can use pi approximately equal to 3.14159. So we multiply 129 by 3.14159, which gives approximately 405.27. Therefore, the area of the circle is approximately 405.27 square units. And that's the complete solution. The beautiful part of this problem is that we never had to calculate the radius directly.